Hi, I am Nusret, and I will be talking about our paper, Like Clients for Lazy Blockchains. This is joint work with Lei Yang, Dionysis Zindros, and David Che. I would like to start with the dichotomy of blockchain protocols. On one side, we have authenticated protocols, where consensus nodes who are responsible for protocol execution are also full nodes. This means that whenever there is a new block proposal, the consensus nodes download the transactions in the block, verify their validity, and if all transactions included are valid, treat the block as a valid proposal. In this case, the block will be finalized. This is repeated for future blocks. Now, if there is a new block that contains an invalid transaction, upon realizing that the block is invalid, the consensus nodes will refuse to finalize the block. As a result, the next proposal with a valid transaction will be extending the tip of the valid finalized chain. Note that all of the finalized blocks contain valid transactions. As a result, the ledger of an authenticated blockchain protocol simply consists of the transactions included in the finalized blocks. Many blockchain protocols fall into this category, the prominent ones being Bitcoin and Ethereum. On the other side, we have lazy blockchain protocols. In a lazy blockchain protocol, the consensus nodes that execute the consensus protocol do not care about the validity of the transactions included in the blocks according to any external validity conditions. In this case, they will finalize a block if the block is syntactically correct, even though the transactions included might be invalid with respect to the previous transactions. As a result, the blocks with invalid transactions will also enter the finalized chain. In the case of lazy blockchain protocols, the burden of weeding out invalid transactions and creating a ledger of valid transactions falls onto full nodes. Full nodes download the transactions in the finalized blocks, execute them one by one with respect to the latest state of the blockchain, and obtain the ledger of valid transactions. Some prominent examples of lazy blockchain protocols include Colored Coins, BRC20, and Celestia. Not all nodes on a blockchain ecosystem are full nodes or consensus nodes, but there are also like clients who would like to learn about a small portion of the blockchain state or only a single transaction within the finalized ledger. Authenticated blockchain protocols provide a simple payment verification protocol to support like clients on them. Let's consider the example from the previous slides. Suppose there is a merchant named Bob that is a like client and would like to sell its car. On the other side, we have adversary the buyer, who is a full node and it would like to double spend the same coin to buy Bob's car and potentially some other merchant's car. In this example, adversary tells Bob that it has paid Bob through transaction 2. Then, before handing over its car, Bob asks whether the transaction 2 is included in the ledger. Now, because this is an authenticated blockchain protocol, all transactions that are within finalized blocks will eventually be included in the ledger. Thus, it is sufficient for the adversary to point at a finalized block containing transaction 2. Once the adversary does this, Bob will gladly hand over his car. Now, suppose adversary tries to double spend the token that was paid to Bob with transaction 2. Now, adversary also tries to buy Alice's car and tells Alice that it has paid Alice through transaction 3 within this block. Now, because transaction 3 is invalid given transaction 2 that appeared before, the block containing transaction 3 will not be finalized by the consensus nodes. As a result, adversary will not be able to point at a finalized block once Alice asks the question whether transaction 3 is in the ledger to convince Alice that transaction 3 is indeed in the ledger. But what happens if we use the same SPV idea on lazy blockchains? Now, here is the lazy blockchain example from the previous slide. The interaction between the adversary and the Bob is the same as in the previous case. However, now note that when Alice asks whether transaction 3 is in the ledger, if Alex simply uses the inclusion of transaction 3 within a finalized block as a proxy for that question, then she will be easily convinced that it's in the ledger, because adversary will be able to point at a finalized block of the lazy blockchain containing transaction 3, even though transaction 3 is invalid. Unfortunately, this is a double span, and this tells us that the SPV-like clients do not work on lazy blockchains. The purpose of our work is to support like clients on lazy blockchains. For this purpose, we provide an optimistic and interactive like client protocol on lazy blockchains. Let's consider our client Alice from the previous page. In our new example, Alice asks about her account balance. To figure out the answer, Alice connects to multiple full nodes. She assumes that at least one of the full nodes is honest, whereas the remaining ones could be adversarial. In this example, first, all full nodes give the same response. Then Alice can rest assured that the response given by the full nodes is the correct one, since the honest one must also be giving that response. But now, when the full nodes disagree on the reply, Alice has to figure out which full node is being truthful and which one is lying or is under adversary's control. So this is the question we will try to answer with our protocol. But before stating the details of our protocol, let's state its security guarantees. Suppose the like client connects to n full nodes, and at least one of the full nodes is honest. We assume that its identity is unknown. This set of requirements is also known as the existential honesty assumption. We assume that the network is synchronous and denote by L the number of transactions in the ledger. Then, our protocol ensures that the light client can find the correct answer to its queries in order n log L rounds of communication with order n log L communication complexity. Moreover, full nodes can serve multiple like clients with a storage and compute complexity of order L. To formalize this statement further, by correct answer, we mean the answer given by the honest full nodes with the longest ledger amongst the connections of the like client. This definition becomes more important when the like client connects to more than 2 full nodes. Next, to convince the like client that the response given by it is correct, the honest full nodes construct an object called the dirty Merkle tree. Here we observe the lazy blockchain example from the previous page. We call the sequence of transactions in this blockchain the dirty ledger because it contains invalid transactions. Now, each honest full node executes each transaction one by one with respect to the latest state of the blockchain. And it groups together the transaction along with the root of the state obtained after executing the transaction. In this example, there is a genesis state committed by ST0, and upon applying transaction 1 on top of the genesis state, the full node obtains state 1, and ST1 is the root of the state 1. This is repeated for future transactions. When there is an invalid transaction with respect to the previous state, the full nodes do not try to execute this transaction, but simply copy over the previous state into the next tuple. Now, this is done for all of the transactions in the dirty ledger. And finally, honest full nodes build a Merkle tree on top of this sequence of tuples. Now, let's go back to our example where the like client was trying to figure out the correct response. Without loss of generality, let's assume that the right full node is under adversary's control. To convince that its response of $7 is correct, the honest full node gives the like client a dirty tree root along with a dirty tree proof. This dirty tree proof verifies with respect to the given root and the latest claimed state root. To play along, the adversarial full node also gives a root and a proof. Since this root also verifies given the latest claimed state root by the adversarial full node, it must be the case that the dirty tree root given by the adversarial full node is different from the one given by the honest full node. This basically reduces the light client's queries to figuring out which 33 root is the correct one, namely the correct one corresponding to the lazy blockchain. To answer this question, the light client runs a bisection game. In the bisection game, it acts as a verifier, whereas the remaining full nodes act as provers. As part of the game, the verifier asks questions to the provers, and the provers reply through the same channel. The prover loses the game if it does not reply within some timeout period. Now, going forward, let's assume that none of the provers time out, and in this case, the goal of the verifier is to identify a point of disagreement between the two provers. Let's see the bisection game in action. Here we see the two provers from the previous slide. The verifier, upon observing that the two 33 roots are different, will ask the two provers to reveal the two children of the 33 root. Upon observing the two children of the 33 root, again the verifier compares them, realizes that both of them are different, and continues its query on the left subtree here. And then the process is repeated for the left child up until the verifier identifies a point of disagreement at the leaves of the Merkle tree. At this point, the verifier observes that the two provers agree on the transaction's state root tuple at this position 3 of the sequence of tuples, whereas they disagree on both the transactions and the state roots at position 4. The identification of this disagreement reduces the verifier's protocol to basically figuring out whether transaction 2 is followed by transaction 3 or transaction 3 prime, as claimed by the two provers. To answer this question, the verifier can consult the lazy blockchain, as was done in the SPV example. Upon observing the lazy blockchain, the verifier realizes that TX2 is followed by TX3, not TX3 prime. This means that the prover on the right-hand side, the one in the adversary's control, is indeed lying. And the account balance asked by the verifier should be the $7 response given by the left-hand side prover. Now, let's assume both transactions claimed by the tuple at the point of disagreement were the same, in which case TX3 and TX3 prime would be the same, but the state roots included within the tuples were different. In this case, the honest full node to prove state transition can use the same method as fraud proofs as was identified in this earlier work. For this purpose, the prover can create a proof that shows that ST3, as claimed by the honest prover, is valid given the previous state root ST2 that was agreed upon by the two provers and the transaction 3. Finally, we report on an implementation of our protocol with 17 provers in 17 data centers globally. We consider a verifier that's a commodity laptop with 300 megabits per downlink and 10 megabits per uplink bandwidth. We also consider a 33 of 300. Here we observe the graph of a protocol duration as the ledger length changes. As you might observe, as the ledger length grows exponentially, the protocol duration grows only linearly, matching our logarithmic claim. To give more concrete numbers, we observe that for 10 million transactions, 16 games, namely 16 bisection games, and 4 rounds of interaction per game, the protocol duration is only 18 seconds. This is comparable to many blockchain protocols that confirm transaction with latencies of tens of seconds. Now, you might ask why we picked 300 as the degree of our Merkle tree, whereas our examples only had degree of 2. This is indeed guided by our implementation and experiments. As we observed before, when the 33 degree is small, its height is large, which means that there are many rounds of interaction between the provers and the verifier. This makes the protocol duration large due to the network delay. On the flip side, if the 33 degree is very large, each round of interaction requires communication of a large sequence of messages. In this case, the bandwidth of the verifier becomes the bottleneck. And finally, we observe that this latency of our protocol is minimized at optimal 33 degree of 300. Finally, I would like to talk about verifying the state commitments. We observed an optimization could help provers prove transitions if we basically batch transact and prove state transitions on a per block basis. If we do this, the provers can also use EVM's public RPC APIs, more specifically the debug trace block API. In this case, the state transition proofs are bounded by 10 megabytes for recent Ethereum blocks. They can be downloaded in less than 0.3 seconds, and verifying the next state root takes at most 0.8 seconds per block. In comparison, a full node syncing with the latest EVM state takes at least a full day and uses 540 gigabytes of SSD. So I have presented the first light client construction for lazy blockchains. And for more details on ledgers with different sizes and verifiers connecting to more than 2 provers, please consult our paper. We note that our protocol requires no trusted setup and no consensus changes. We also highlight another application of our protocol beyond lazy blockchains to optimistic rollups. Note that most optimistic rollups confirm transactions with a latency of a week corresponding to the dispute delay for fraud proofs. During this time, transactions added to the tip of the rollup ledger might contain invalid ones. Thus, the rollup light clients can treat the tip of the rollup chain as a dirty ledger and can use our protocol to operate at the forefront of the rollup chain. Thank you.